So our next speaker is Kristóf Benedek, who will talk about the synchronization and topological analysis in European high voltage grids. So the stage is yours.
Thank you. I'm delighted to be here again. I presented already some of our results last year, so it will be kind of a continuation of that talk, but or not, there will be reminders. So I'm a physicist by nature, not informatics, so I will talk more about our results, what we obtained using GPUs. So why synchronization? Synchronization is, first of all, a fascinating area in physics that appears in everyday life, and not only in everyday life. Like you can think about fireflies, how they're flickering synchronizes, candles can synchronize, but brain networks, neural networks can synchronize, telecommunication can synchronize, transport and electrical power grids can synchronize. And the very nice thing about this is that the demand usually and the source, the supply, pushes these systems to self-organized criticality, and these systems operate there. And you can observe fascinating phenomena that and different kind of universality classes and universal behaviors in these systems. And I will talk about synchronization in power. This is maybe one of the most notorious example why this is important. Here you see the biggest blackout perhaps in history that occurred in 2003 in North America, where basically on the East Coast it just went black. Like here you can see Boswatch. This is a picture before the blackout, and this is a picture after the blackout, and then you can see the difference that, well, there is no light. And what was the reason behind it? Because high voltage power grids are usually operated by frequency control. If the frequency control, if the frequency of the nodes is just out of an interval, then the operators have to come in and they have to shut down the nodes in question to not get interference, to not destroy the whole system. And this will be a movie that will not work because it's not on my my PC, but the starting point was here. See, this node is the faulty node, this generator, and it was not remedied. And by the time it caused major interferences in the whole network, and the whole network just crumbled. So about motivation, what do we want and why do we want it? Well, of course, stability and robustness, synchronization, and how the topology of a network can influence each other's, and moreover, how the heterogeneity of the parameters can influence the synchronization in such a network. Of course, we want to model the dynamics, and this will come into the picture. Then I will talk very briefly about databases. My talk last year was mostly about this, and some about the topological development of the network. How can we make a network more robust, stable, purely by investigating the dynamics and then implementing some topological changes. Yes, and then let's start off. So the basics, mathematical idea to understand the graph. What is a graph? Graph is composed of two sets, vertices and edges. Vertices describe the nodes in the network, and edges basically the links, the connections between such nodes. And if you have such a mathematical construction, then you can define already different quantities on such networks, like degree, the distribution of the degree, the adjacency matrix, which is another representation of the graph, clustering coefficient, modularity ratio, whatnot. And yes, well, we had some real world data about how our networks look like, but weighting in such a power grid is very important because not all the connections are equal. You have connections that are that operate on higher voltage, others not, and this comes into play when you weight the network. And my last talk was about this, how we weighted this network and how we this skeleton data into a whole data set, basically. And dynamical modeling. So this is a part which relates to GPUs, because the whole system's dynamics is described by the so-called second-order Kuramoto equation, which is a second-order differential equation. And here is what it looks like for a node I. So theta is just the phase of one node I. Then you have different parameters like pi, which is the power source of power of source or sink. Then you have this fraction, which is basically this k coupling. Then you have the elements of the weight matrix, which is just the adjacency matrix. Then you have the sinusoidal term, which basically measures the interaction between neighboring nodes. And why GPUs? Because like on the scale when you have a system of thousands of nodes only, then you can operate on CPUs. But when you get to the scale of tens of thousands or even larger, just think about connectome, not even human connectome, but hemibrain connectome, fruit fly connectome. You have a couple of few 100,000 nodes there and millions of links. Well, in that case, you cannot rely anymore on CPUs. You have to make use of the force of the capabilities of GPUs and massively paralyze your problem. Otherwise, it will just take ages to run the simulation for sufficiently large time step, because you have to thermalize first your system, then you have to actually play the dynamics. So you start your system from some initial point, then you have to let the dynamic to play its role to get into a thermalized state, and then from there you can observe the interesting phenomena. Yeah, so that much about GPUs, and now I return back to the physics. When you have the system and the dynamics defined as such, then you can define pretty much the usual order parameters, like the global phase order parameter, the frequency spread, and the whole dynamics after the already mentioned thermalization phase is governed by a threshold dynamics. So we will just go check this interaction term, and if this interaction term is larger than a given threshold value, then we just say that the line between the two nodes is overloaded, and we will just cut it. And this somehow is similar or can be equal to the frequency operated real-world networks. And here you see the three of our systems: the European 16 high voltage power grid, the European 22, and the United States 16 power grids with the corresponding number of vertices and nodes. And this did not update. Okay, never mind. I think I had an updated version of this, but then not. So this is the adjacency matrix for the three systems, and this can be showed in a different representation. You can make it more diagonal if you order the nodes with respect to which community they belong to, and then you can see the modular structure of these networks better. But you can already see, mostly in the case of the EU16, that some kind of modules are here. This diagonal structure, it also shows already some modularity, and these lines here too. And what we did is, firstly, we did not touch the dynamics yet, but we checked how the network is structured, and we checked the degree distribution of the nodes, the length distribution of the nodes, and we observed that these are somehow forming universality classes because they obey already some kind of power laws. And when a physicist gets a power law, then his eyes are just lighting up that, wow, this is some kind of universal behavior And yes, this is somehow what we expect, because if you think about a power grid system, then that should be somehow a hierarchical modular system. You had sometimes at the beginning of the times a generator or a source, and you built something around it, and then you developed it further and further. And we see this kind of universal behavior in all three of our data sets. And next, we analyze also, this is the notorious link distribution, and here the admittance probabilities. Now, admittance is interesting because admittance is or was used mostly to weight our networks, and also these distributions, well, not on the whole domain, but on a big part of the domain, shows these universal behaviors. So what about the more in-depth structure of these networks? When you have a graph or a network, then you will try to somehow look at the community structure of a graph of a network, and if it has to do something with like in our case with the real world data, and if you look at it, then it has, because it is mostly influenced either by political borders or by geography. Just look at the UK or Spain, or by history, because here you can see somehow exactly the line between Germany and Eastern Europe, the print of the Iron Curtain. But surprisingly, you don't see these or all of these in the EU22 data set. So this also means, all right, our networks are evolving, so part of these boundaries are changing. So these are not really static, and we can compare these two networks to see what was the effect of the disappearance of these boundaries. So okay, we had this, we had the dynamics, we had the community structure and the structure of our networks, and we play the dynamics. We check the nodes, we check the order parameters, and what can we say? Well, just by looking at the local order parameter or the global order parameter, you can say one of the nodes is either weakly synchronized or strongly synchronized, solely depending on the level of this local order parameter. The local order parameter, I did not really specify, but if we very quickly go back here, then is this guy here, which is very similar to the global, but in the global order parameter, you sum up for all the nodes, this exponential term, and here you sum up only for the neighbors. Okay, and when you identify these weakly synchronized nodes, then you come up with some idea how can you change your networks to be better. And if you are a network scientist guy, then you say that, okay, let's build triangles, because triangles are good. They make your network more robust. And why? By just simply thinking, you will have alternate routes to reach this node if one of the links is destroyed. And we exactly did this. Or if two weakly synchronized nodes are neighbor, then we just double the links. So this bypass method of improving our network is dependent on the dynamics. And we had another method, which is the bridge method. It depends on the community structure. We identify the communities, we can identify the links that connect the different communities and just strengthen these. And here, you can see the results of the bypass method applied to the EU16 and the EU22 networks with yellow lines. Those are the newly added links to the network. And yes, here is the bridge method, which I mentioned. Just strengthen the links that are connecting different structures, substructures of your network. And here you see again a different representation, more abstract representation of the communities. And the bridge method entails that you can see these faint lines between the different communities. Now we are strengthening those. Okay, and we play again our numerics, our dynamics. And we expect that we get at least better synchronization and less frequency spread. And if you check this for the EU16 for a given damping parameter, then you can see that even for the bypasses or for the bridges, the synchronization level just increased compared to the standard system, and also the frequency spread decreased, and the number of line failures, they also decreased. And this is something what we wanted, because we don't have that many line cuts. Our synchronization overall is better in the network. So the power supply, if you want, is more stable in our network. But also, if you think about neural network, then just the communication between two neurons is just more stable. Okay, you can ask, how do you want to dig into the brain and add more nodes? Well, that's a question I cannot answer. Maybe a biologist could have at least an idea. And here I want to just briefly show, again, numerical results for the EU22 network. But basically, the conclusions are the same. The synchronization is better, frequency spread is also better, and we experience less line cut failures, especially in this part, right? Yeah. And what else did we discover or notice? Well, when you talk about synchronization, or a hot topic is chimera states in a network. What are chimera states or frustrated synchronization? Well, you have some kind of network, some kind of system, and you look at it as a whole, and then you just look at parts of it. And then you will see some difference. You see that the whole network, the thick black line, behaves somehow, and then substructures of the whole system, they behave differently. And what could be the underlying reason for this? Now, that's interesting for a physicist. And especially in our case, check these red and green lines, which are, especially the green line is much, much below how the whole of the system behaves. And what is the reason behind this? Now, that's what interests me currently and the whole group. And we are trying to investigate this. So yeah, here is already the summary. I included again 2 more slides in the latest version, but yeah, technical issues. Now we are investigating this. This is the current point of our research. We have a couple of ideas. In graphs, you can look at the cycle structure of the graph, because cycles are just structures that start at one node and end at the same. And if you investigate this structure, then you can show some light on the redundant structure of your system. Because if you think of it, cycle is just chained together nodes. So that's the first and most simple, most redundant structure in your network. And you can also look at the graph Laplacian for the whole network, and also for the substructures of the network, for the communities, and check how the spectral dimension of these behave. Well, just very briefly, the graph Laplacian is related somehow to the random walk on a graph and to diffusion problems, to the Laplacian operator. And if you apply the graph Laplacian to a graph, then when you have very small angles, so close to the equilibrium state, you will get back basically to a random walk problem. Okay, so that's where our research is currently. And here is a brief summary and outlook, and I think I will stop here to gain some more minutes. Thank you.
Excellent. We have time for questions. So anyone has any question?
I believe on slide 12, Denmark was an outlier. Yeah, 12, I think. 12.
This one?
Here. Yeah. I'm not sure I'm saying it right, but what's up with Denmark? Didn't they take part in the grid evolution? Or
The
what?
Denmark here, you
Yeah.
mean, right? So yes, this is a very questionable part because you see a lot of reds and, well, you don't see yellows, but there are a lot of yellows, trust me. The thing is, you see here these lines. And now these lines are very particular lines because these are underwater lines. And usually your power grid operates with alternating current lines. But these ones are high voltage direct current lines. And of course, here you will have a lot of transformators. You will just transform your alternating grid to direct and vice versa. And that's why you see that many red dots here, because you have a lot of these HVDC lines coming into Denmark from Scandinavia, and also like this part from the UK to Germany, France. Yeah.
I see. Thank you.
Yes.
Technical issue. Probably you mentioned, just I didn't get the point, that all the network has the same voltage and everything are the same, or this has various levels?
Yes, so we are dealing with high voltage networks, but the question is excellent. So also the high voltage is structured into different levels. And this table at the very beginning shows you these levels. So in high voltage, the lowest level is 120 kilovolts. And then the next level is somewhere around 200, 220. And then the very high voltage is at 380, 400. There are some 500 kilovolt lines as well, but they are pretty rare. Yes, it was included. This is all included in the weighting of the lines. Yes. So here you can see how we computed this weight matrix elements, basically.
So is there any other question? If none, then thank you for your talk. And I'm asking Zoltán Simon to come forward.